Hi everybody, welcome to the Spark workshop. It's a small group, so maybe tell me what your interest in Spark is, or familiarity or lack thereof. Sort of where's everyone coming from? Who's used it before? No one. Okay, cool. But people who are interested in distributed computing, sort of broadly, that's the, okay, cool. I basically designed this as a tutorial, but an interactive one, so it's really just a sequence of things that I think we can all do together. That's of course predicated on everyone being able to install Spark on their local machine, which actually should be pretty easy. On the other hand, I don't want to spend the entire hour doing that. So basically what I think we'll do, I'll sort of start saying a couple things about it. We can try to get as many people to install it as possible. In the form we're going to use it is really simple, so we can try to make sure everyone gets up and running, and then if not, just sort of follow along with your partner or follow along with the slides, basically. So Spark is kind of a funny. Let me fire these slides up. Everything for this is in this repo I put together, Spark for Everyone. And this is inside the Neurohackweek GitHub. So if you, at some point, will actually clone this repository, but just for now, know that if there's a reference, all the slides are there in a markdown format. I already kind of introduced myself earlier. I didn't expect to be here earlier, so this bit about me is kind of irrelevant. But we're going to be talking about Spark. Spark's kind of a funny, I think its role, especially in this community, is kind of funny. So Spark you've probably heard about in the context of like large-scale analytics and sort of the business world. It was originally created by a group at Berkeley, basically as a research project on designing some new APIs and new ways of interfacing with sort of parallel distributed computing. And then it kind of blew up. And it sort of, really exploded in various sort of industry, business intelligence. Come on in, we're just getting started. Oh, great. Oh, wow. Whoa. All right. I will try start again.
My soundtrack at this.
Oh, cool. No worries. Get comfortable, everybody. So I said at the beginning the goal here will be to basically do a sort of tutorial style thing, but one in which you're actually doing stuff as we go. So that will involve people installing some things on their machine, but it's pretty simple, and if it doesn't work, I don't want to spend the whole hour doing that. So basically we'll try, and then whoever succeeds will be the person that their neighbor will follow along with as we go. And I'll be basically live coding all these examples up here as well. So maybe show of hands again who's used Spark, if anyone, because we have some new people. Okay, cool. So basically one still. Essentially that rounds to 0. So Spark, I was giving a little bit about its history. Basically, it was developed as a research project at Berkeley by a really cool group. And it is it's a new way of doing certain kinds of distributed computing operations. I think it's, you can think of it as this like crazy big, next big thing, or you can think of it as a software library. I sort of prefer to think of it as the latter. It's not particularly scary, it's not particularly complicated. There are aspects of it that can become complicated. It's become very popular in the sort of business intelligence, companies that need to analyze a bunch of log files or user data, this kind of stuff. It's definitely designed to make certain kinds of operations on very large data sets take much slower or happen much faster by leveraging the computing power of a large number of machines. That, at a very high level, is what it's about. That's what distributed computing is about in general. Spark is really just a library that gives a really friendly, to me at least, very straightforward way of doing certain kinds of distributed operations on data. And one of the really cool things about it is that it has a really nice Python API, which means that if you're doing development and other kinds of scientific analyses in Python, it can be a really easy way to start doing certain kinds of distributed processing as part of your workflow without like switching tools or switching languages, at least not entirely. The main, sort of for reference, Spark grew out of an earlier project called Hadoop, which is basically mainly written in Java. That's the way you interface with it. Hadoop is kind of horrendous to use. Even doing really basic things is really complicated. It was, at the time, a really important sort of step in the direction of simplifying distributed computing, making it easier, making it more accessible. To me, Spark is the next generation, or sort of next iteration in that process. There will surely be more iterations in that process. Spark is, in that line, one of the early things to have a really clean Python API, which is nice because it exposes it to the rest of the Python ecosystem. And we'll talk explicitly about, at least the way I find it useful to use Spark, alongside the kinds of scientific computing Python-y things that you've already been seeing in the course. One note about sort of where Spark runs, which I often sense as a point of confusion. So Spark is really just a library. Most of it is about providing a set of functions to interface with data that is typically distributed across a cluster. So part of the complexity of Spark is just deploying it on a cluster. That's sort of one thing. But then once it's deployed, then there's actually the part of like how you interact with it. So one of the cool things is that if you just run Spark locally on your machine, it kind of pretends to be distributed, and all the operations and all the functions are exactly the same as they would be if you were running it on a cluster, except you don't actually have to have a cluster running. So everything we're going to do today, we're just going to install it and use it on our local machines, and then basically just take my word that if you have it deployed on a cluster and you did all the same things, everything would essentially work the same, except all the operations we're doing would be parallelized across as many cores or as many CPUs as you have available on your cluster. The reason you have to take my word for it is in practice, really that is true. The complexity comes from just deploying it in the first place. I think tomorrow you're going to learn a little bit about just general cloud compute using things like Amazon Web Services to deploy clusters. In general, that is a way to deploy a Spark cluster. It involves a little bit of complexity. It's not that bad. There's some helper tools that people have written to make it easier. We've tried to do a little bit of that. But the cool thing is that we can basically just use it locally. But one thing to be aware of is that running Spark locally, I think some people think it's going to make everything faster. That's definitely not true. So it's really nice because it just lets you test the API and test the functionality locally. But if you have something you're doing in Python and then you just install Spark locally, it's not going to suddenly make things faster. And paradoxically, actually on a single machine, it can make things a lot slower. We're going to talk about why. So that's sort of a weird thing to keep in the back of your mind. After this workshop, don't just start doing everything on your local machine using Spark. It will not be faster. And in fact, you'll figure out really quickly that it's not faster, and then you'll probably stop doing it. It's really, it's only relevant if you are then going to use it in the distributed setting. At least right now. I'm skipping my introduction because I was here earlier. So why don't we get started and try to get everyone here to basically download and install Spark. This is the part that hopefully at least 50% of people will figure it out, but I don't want to take the whole time. So if you go to spark.apache.org and then you go to download, so spark.apache.org/download, and then basically just answer these questions, I think exactly as they are in the default. So you want 2.0.0, pre-built for Hadoop 2.7, and direct download, and then just click that button, then it should start downloading. And it's about 100 megabytes, so we'll see how long that takes for everybody. Is anyone downloading it and can give me an estimate on how long?
2 minutes.
2 minutes? Okay, great. That's not so bad. Cool.
Yeah, 2 seconds.
3 seconds.
Really?
Yeah.
For 100? Seriously? What
Depends what Wi-Fi.
what internet are you on? Holy shit! What?
Roam.
Sorry.
Yeah. Really does.
Whoa! Oh, the microphone's not on. That download is going really quickly. That's crazy. I should go download some movies or something. That was a joke. Okay, cool. So once you've downloaded that, You can just put it anywhere. I usually just put it in a folder called code. But basically, yeah, just unzip that folder and put it somewhere. Yeah?
I just want to say, if anybody else like me is using Windows, Google is telling, a quick Google search is telling me getting Spark up and running on Windows could take more time than,
Oh, really?
yeah. Just,
Than the sort of Mac. Okay, so maybe we'll make a preemptive decision that if you were on a Windows machine, find a neighbor who's on a Linux or Mac machine.
I was just getting the feeling that it could
Okay,
not
that's
work.
entirely possible.
Yeah.
Yeah, thank you for doing that. I've not tried to do it on a Windows machine. I should.
They're long.
Long blog posts, great. Love a good DevOpsy blog post.
So the one option might be if you already installed Docker from the morning tutorial session.
Oh boy.
Oh,
Yeah. In a.
you were under Docker.
Yeah, I mean, 10 points to anyone who gets Docker plus Spark on a Windows machine working. That'd be great. I mean, that's how it should. That's how we should do things. In practice, I can imagine it's not super straightforward. Once you have this thing in a folder, we should do basically the first thing to check that it's working. The one other thing you have to do along with downloading it is to, well, actually, answer the following question for me, everybody. Who has modified their bash profile before? Okay, cool, great. Not everybody knows how to do that. So basically, you want to add this to your bash profile. This thing that says PySpark driver Python equals IPython. Well, the cool thing is we'll figure out really quickly if this is working and sort of debug it. Basically, the thing to do is to, everyone see this okay? So I'm in the folder that I just downloaded, and I'm just going to do /bin/PySpark. And if everything's working, then it should start the Spark command line tool, and you should be in what looks like a typical Python environment or an IPython environment. And except it should say this. Yes.
Can you go back to what we had to edit in our bash RC?
Oh yeah, it's this line.
Okay.
All this does, if you didn't do this and you do the thing I just said, then it will start Spark in the normal, like whatever your default Python is.
Oh, okay.
So that's fine too. I just like having used the IPython, not the notebook, just like the IPython shell instead of the generic Python shell. I can never go back to. I mean, like it doesn't even have, the basic Python shell doesn't even have like,
Paste.
yeah, paste or tab completion, yeah. Yeah, you get used to nice things. So yeah, but that's all we're doing is setting an environmental variable that tells Spark to launch using IPython instead of Python. To sort of demystify a little bit what we're doing when we start this command line tool, I honestly don't like that they do it this way. Basically just because I think it adds a little bit of unnecessary complexity. But all we're doing is we're basically launching Python, but before launching Python, that thing that we called PySpark just like starts up a bunch of scripts basically that sort of configure Spark appropriately. I would sort of rather do that like once I've already started the shell, but doesn't matter. Is anyone looking at something that looks like this?
Java issues.
Nice. Java issues? Oh boy. Okay, cool. All right, so we'll like take 5 minutes to try to get as many people going as possible. But then again, you'll have neighbors and you'll have me.
Trying to update. You can see that.
Oh, just to update Java? Yeah. Great, so you might be asking yourselves, why, if we're doing something in Python, does it matter what Java version someone has on their computer? That's a great question. That's because Spark is kind of weird because it's actually written for something called the JVM, and Spark itself is written in Java, but we're interfacing it with it from Python. So it has a Python API, but the actual core code is written in Java and it's running on the JVM. There's a long history of using Java for doing sort of distributed systems development, and that's why, well, there's a longer probably explanation, but that's why Spark itself is written in that language. There are some exciting new projects that are sort of pure Python libraries to do some of the kinds of things that Spark does. One is called Dask. I hope that in maybe 2 years we'll do that tutorial as well. For certain kinds of workflows, it's not quite as mature as Spark is. That's why, at least for a lot of the stuff we do, we don't do a lot with it yet. But yeah.
Could you go back one slide?
Sure.
No,
Forward.
that one.
Great.
PySpark driver equal to IPython.
Yeah, again, if you do, it should still work if you don't do
It
this.
just gives us the normal.
It just gives you the normal shell. Yeah, exactly. Not at all.
Browser is. It says it doesn't like Chrome.
Oh, really? When is it saying that?
After you do the install, it's like test to see that the Java runtime version.
Oh, weird.
I tried restarting the browser.
It's a weird Java problem.
Okay.
I'll come over. All right, everybody help each other out, and we'll try to get as many people going as possible, and then we'll kick into it.
This is basically the issue. So I do install, it says it installs, everything's cool. And
Crazy.
Then, I mean, I could try using it. I just don't know how it knows, like,
So you put it, did you put it somewhere?
yeah.
Do you, yeah, okay. So, oh, no Java runtime. Ah, okay, so
I did this.
you did this.
Yeah.
And what happened?
I did it twice. It
Oh, really?
actually installs, everything's cool.
Oh, really? Can we start, have you started a new terminal since you did that?
I did, but you
oh, really?
try doing it again.
No, I believe you.
Yeah, if you go to more,
This is what you did. Yeah. Okay. Great.
so you've not seen this error then?
No, this is crazy. I mean, this is why. Do you have another browser?
I do.
Do you have Firefox?
Maybe
Safari?
I just got this computer.
It might, yeah, I mean, it might
I
be
have
better Java.
Interesting.
Firefox at the moment.
I think it's hard. I mean, so if you
I have it downloaded there. I mean, you have to be downloaded.
Oh, interesting.
sourced it, oh, and it's only in, yeah, because iTerm runs a separate instance. Yeah.
It's good that it didn't. Oh, okay, cool. Because maybe we want to do it. This is crazy.
Can you force it to use a particular browser? I don't understand why it needs a browser. That's what I can't figure out.
I mean, yeah. So like,
I did this. This is what I
yeah.
did.
Okay.
I'm not off because I don't want that. This is now my third install, so it's going to be extra Java.
You're getting juiced up on Java. It is
So
coffee.
you do this,
Okay.
And then it's going to open it in Chrome.
Okay. Let's try in Safari.
Oh, good. Okay.
I mean, this is weird.
Verify Java. Well, maybe if we hit trust here, that doesn't even make sense either.
Maybe it maybe it needs to run this verification. I mean, if not, yeah. I don't know. Find out in a second. Okay.
Let's see.
Now open a new browser. No.
Alright, let's try restarting the terminal.
Yeah. This is really weird. Is that what it is? Yeah. Okay.
No.
It's a bummer. You can definitely Google this, and there might be something. But if not, maybe just follow along. Sorry. Yeah. No, that's super weird.
We need to install the JDK.
Yes, potentially. And there could be weird issues associated with that. You're on a Windows machine?
Yeah.
Yeah? Oh, you listen? Oh, okay, cool. Is it working?
Well, I don't know what I'm doing, so
Okay.
I untarred.
Did you okay.
And I just did it. Okay.
That's cool. Oh, nice. You have, yay.
Yeah, we just installed it, so we should hit it.
Okay, cool.
I don't know what I'm doing.
Oh, sorry. So just do, I should put up the next slide. All right, I see at least some sparks on people's screens, so that's cool. This is the next step. Just typing .bin/PySpark. So let's see if that works. it'll be ./bin. Yay, okay, cool.
So everything's fine?
Everything is it using IPython or is it using? Okay, it's using your generic Python.
Okay. Well,
So maybe that didn't,
thought I
that
fixed
changed,
that
didn't it? Interesting. Yeah, right. Show me your bash profile. Oh, maybe you need to open a new terminal.
so put it at the bottom.
Okay. Yeah. Oh, say export. Yeah. Cool. Okay. Oh, and then start a new, open a new terminal.
Okay.
Yeah.
We can just source it.
Yeah, or you can just source it.
So can I use it from here, or do I have to start a completely new?
Start, yeah, why not? Just. Okay.
What was the?
And then just .bin/PySpark. Oh, do you have Python installed?
Yeah.
Or IPython? IPython?
I don't know if I have IPython.
Ah, okay. Do you pip install IPython?
Okay, can I just?
Or apt-get? Yeah, that should work. Yeah, try that. If not, I would then, yeah, if that doesn't work, you could just delete that from your bash profile and then just use normal Python. Cool. All right, I think I saw enough people with something that looked like they had Spark running that I think we'll probably get started. But if you didn't and you want to get it working on your machine, I can sit with anyone for as long as it takes. Up to some reasonable limit of time. I'll like stay up till 2 a.m. maybe, trying to get it working. Then you have to give up at some point. But yeah, we can totally get it working later. And then using some of the things you learn in this course, you may be able to do a deployment of Spark on a cluster. But again, today, everything we're doing is local. So I'm really just going to step through what I see as sort of the main like cores, the sort of core thing that Spark is for and is useful for. And if you go read some guide about Spark, you might see there's surely going to be overlap. They might emphasize other things. This is based on my experience trying to use it to parallelize certain kinds of operations that show up in typical kind of scientific Python workflows. For us, that comes from the domain of like image processing and time series processing, a lot of stuff where you're like using NumPy and using scikit-learn and stuff, and you just want to have the ability to parallelize certain kinds of operations. So I'm going to be explaining it from the context of someone who does that kind of stuff, which hopefully should sort of resonate with a lot of what you're thinking about. But definitely jump in and ask questions as we go. So the first thing is what I think of as sort of the hello world of Spark, and this is a great thing to do because if this doesn't work, then nothing will work. And that's especially true in a setting where you've deployed on a cluster and you're using Spark on a cluster. This is a great way just to test that everything is basically functional. So what we're doing is we're creating what is basically the fundamental kind of unit of Spark, or the fundamental data object, which is something called an RDD, or a resilient distributed data set. And the first line, we do data equals sc.parallelize. All right, so I'm gonna hop over here and do it. So data equals sc.parallelize, and then you can just give it a list like that. And what you now have, if you just look at data, we have parallel collection RDD. All right, and if we do data.collect, it should give us back something that says 1, 2, 3. If it doesn't, something is broken, either we made a mistake, or in the more common setting, something is wrong with your Spark installation. So we just did something that probably seems completely idiotic and trivial, which is we made a parallelized data set, basically of 3 numbers, and then that, in this case, is all just locally on our machine, which even makes it weirder. But in general, imagine that you have a big cluster of machines, like 100 CPUs, and you have data, you have something local, and you want to make a collection that's parallelized across that cluster of machines. In this case, that collection is literally the list 1, 2, 3, but it could be anything, and we'll see that in a second. So we're going to distribute this list across the cluster, and then collect says, bring all of that back to me locally on my machine. Now again, it's a little weird because here everything's local because we're all just on our computers. But in general, when you do this operation, that's what you would be doing. So sc.parallelize says make a parallelized distributed collection of whatever I give it. In this case, just the list 1, 2, 3. That's data. And now when I do data.collect, I'm saying bring all of that back down to me. All right, question?
Will it retain the original order? Like if you were performing a process on something and the processor finishes first, or will it change?
It's a great question. In general, there's no guarantee that the order will come back the same. But there are a variety of things we can do and actually put in the data that we parallelize to know something and have some guarantees about its order. When we talk about keys later, that will be very relevant to the problem of ordering. Yeah, it's a great question. Yeah, because in general, the way to think about it is that you're just sort of like throwing these items out into a big sea of CPU, and then you're sometimes bringing them back. So again, this is a great thing to do just to make sure that everything is working. One thing that I find people find confusing, I find it confusing, you might have been like, what is SC? Where did that come from? So remember, we started this by typing bin/PySpark. That is essentially what got created when we did that. So I think it would have been a little more natural for you to like start IPython the way you normally do, and then run something within to get SC, but the way they prefer to do it is you start this command line tool, and then SC is just defined. And SC is the thing that if you were running this on a cluster, SC would capture some of the configuration necessary to be talking to your cluster, whereas now it's just talking to you locally. And in fact, I think if we type sc.master, it just says local. In general, if we were on a cluster, sc.master would be the IP address of the master node of our cluster. Okay, cool. So we all just did the most basic thing in Spark. Once you have these objects, these RDDs, this distributed data object, really at the end of the day, there's sort of two kinds of things you can do on them. And these two operations basically encompass all of distributed computing. That's kind of an enormous oversimplification, but it's also kind of true. So the two operations are called map and reduce. For a history of them, really the best starting point is a paper about something called MapReduce, which was really a technology, sort of an abstraction developed by Google, some engineers at Google, including Jeff Dean and others, back in like the early mid-2000s. That then led to Hadoop, and then Spark is sort of the next iteration. The basic concept is really is quite simple. Map is the process of taking all the elements in our collection and doing something with them. Typically that something is applying a function. So these concepts didn't even originate with computing. They come from basically like functional math. So the idea is we're going to do the same thing we did before. We're going to make our collection 1, 2, 3. But then instead of just collecting it, we are going to first call .map lambda x colon 2 times x. You've seen the lambda stuff, we saw it in the last talk, so people are, basically we're just defining a function that takes x and returns 2 times x, and then we're going to call collect afterwards, and what we should get back if we do this, so if we do data.map lambda x colon 2 times x dot collect, we should get 2, 4, 6. So all we've done, again, this might seem idiotic, we've put the numbers 1, 2, 3 into this big collection of CPUs. We've told it to, in that big collection of CPUs, apply this function, which multiplies everything by 2, and then we're bringing back the result. So hopefully you can already think to yourself, the reason this might be useful in a real setting is that if this collection was really big, so instead of just 3 numbers, it was like 10,000 fMRI maps, and the operation we're doing is not just multiplying by 2, but it's something kind of complicated that takes a long time, then having all these machines in parallel doing this operation is going to be really useful because it'll finish faster. Obviously in the case we're doing now, it's completely trivial, and you would never need anything more than like a CPU from 10 years ago could do this really quickly. So we're not going to benefit here. But does this aspect of the API make sense? All right, there's one other thing that wasn't on the slide, but is actually one of the coolest things, but also one of the most complicated, so I don't want to spend too much time on it, but I want to mention it now and then sort of be thinking about it as we go. It's a little hard to demonstrate it correctly unless you were on we're actually on a cluster. But if you just do this, say data2 equals, or mapped, let's call it mapped, data equals data.map, lambda x 2 times x, and we do that. That happened instantaneously, and if we were on a cluster, or if we had a really big data set, or we had a really complicated function, it would also happen instantaneously. All right? That doesn't mean that in that instantaneous moment, whatever function we're applying actually took place. Because the way this whole thing works is that what you're really doing when you call things like map is you're setting up a sequence of computations that when you actually go to request a result, it will then execute all of them, all the ones up to that point. So when we did map data equals data.map, in some sense, nothing happened. This multiplication by 2 never happened. That hasn't happened yet. When we do mapped data.collect, then it actually happens. So the reason this is really cool, this is a concept called lazy evaluation. The reason it's really cool is because, not necessarily in this example, but let's say I express a long, complicated sequence of operations, all of which are basically map operations. So I say map this function, and then map another function, and then another function. And then at the very end, I say collect. What Spark will do is it will say, oh, all these things you're doing, we'll just do them all at the same time. And that will make it much faster in terms of how much data is getting moved around the cluster. Because whenever we're doing distributed computing, the most expensive thing is moving stuff around. Because you've got 100 machines that you all want to be working on these problems, you want to minimize the movement of data. So the ability to basically set up the whole sequence of what you want to do, and then have Spark say, all right, this is the most efficient way to sort of do this work, given what you want to achieve, and then have it solve that problem for you, and do it as efficiently as possible is really valuable. And that's possible because for a lot of things like map, we don't really need to know the answer yet. We don't need to know the answer until we do something that requires actually getting the answer back. All right? That's a very unintuitive concept, this idea of lazy evaluation. We've said it, think about it, it'll show up a few times. And in general in Spark, it turns out there is a divide between operations that are lazy and operations that are not. So we've actually already seen 2 operations, collect and map. Map is lazy, collect is not. Because map doesn't do anything, collect does something. That's the way to think about it. All right, so we did map. Any questions about mapping? Basic idea makes sense. So you might be wondering, what do you do when you don't have lambda functions, or you can't write a lambda function, because there are certain things in the world that can't be expressed in one line, unfortunately. It's pretty easy with Spark's API just to write a function as a standalone definition, and then plug that into the map operation. So here, we're going to write a function called robot, and the way robot's going to work is if x is less than 2, then it's going to return beep, and if, otherwise, return boop. And if we define robot this way, and then we do data.map robot.collect, we should get back beep, boop, boop, because 1 was less than 2, so we got beep, and the other 2 gave us boop. So this actually makes it, to me, like very syntactically nice to use functions and map operations. Again, just to be thinking about real-world use cases, maybe data is a collection of fMRI volumes, and this function is the operation that registers each one to some reference, for example. You could literally write your little function that does that, and then just call .map and apply it to all the elements in a distributed way. Question?
So because you were saying map is not actually doing the thing it collect, is there any advantage to like actually saving something as an intermediary pointer to it and then doing collect, where chaining is fine?
Yeah, great question. Yeah, so let's say we had like robot 2. So you could do it this way. You could also do data 2 equals data.map robot. This is perfectly fine. This doesn't, one thing people, so this doesn't, there's no cost to doing this.
There's no like advantage preferred.
There's neither an advantage nor a cost, basically. If it makes your code cleaner to have, and we'll do this later, to have intermediate results, then that can be useful. But if it doesn't, then just chain them together. And yeah, often it can be, you might have like images.map register.map. What else do you do with images? Filter. Map statistics. Map results. I don't know. Yeah, I mean, you can just chain all these things together. And there's also a sort of corollary to that. Let's say actually we did this, images.map register.map statistics. One really cool thing is that it's going to try to do as much of this in memory as possible. So in a lot of earlier, well, actually, there's a lot of other approaches to distributed systems like this. What you would do to implement this is you would first register all the images, and then you'd like write that out to a bunch of temporary storage. Then you'd reload everything, and then do your statistical calculation. But Spark can basically, again, because this doesn't happen until we get the result back, Spark can say, oh, cool, you want to first do registration, then statistics? We're just going to do those together while the whole thing is loaded in memory. And it's going to be way faster than if you're constantly loading and reading stuff from disk, because it's much faster to access stuff from memory than from disk.
And
yeah.
is it going to, for each element in like an array like this, is it going to run each one as soon as it's done? Or is it going to wait for the entire thing to finish one step? So for example, imagine the second map step was like some product or a group mean or something, and you wanted to scale everything.
Yeah.
Wait for everything to finish before it goes to the next mapping operation?
It can. That's a good question. Partial results can proceed to subsequent stages. Depends. If you're only doing maps, I believe that's true. Yeah, the way to think about what it's doing under the hood, so yeah, Spark has a scheduler, which is basically what takes these things we're giving it and then actually translates that into work that gets executed across the cluster, and it does that very well. If it didn't do that well, we wouldn't use it, basically. For something like this, the way to think about it is that it's basically just coming up with a single function that does both of these things, and it's just running that. It's as though you just called, in this simple case, it's as though you just called like map crazy function, where crazy function does a combination of these things. So it's not really going to have to wait to do one, it's not going to have to wait to do all of them before doing all of the subsequent ones. So it's a great example of why that kind of is called pipelining, of kind of combining stages smartly can give you big gains in efficiency. Great question. Yeah.
How does it handle
Oh yeah. So the way it handles exceptions is not very, I would say not very well. It does something. So basically, I mean, we can just watch it now. It gives a lot of errors, basically. So let's write a function def mistake.
So for example, the robot function that you had, if in the else clause you just raised error.
Yeah, right. We can just do that now. Oh wait, let's just do like, let's define something that doesn't exist, like print foo. Okay, cool. All right, so now data.map mistake.collect. Okay, cool. So yeah, it baffles me that after like, Spark's been around for this point like 4 years. Why there's not a better error message. So the funny thing is, the only thing you need to know here is in one line, and it is actually in one line, but you have to wade through just like enormous amounts of garbage. I can try to explain why this is true. I would have a hard time justifying it. At the end of the day, yeah, basically there is the error, which is literally the error that each worker, essentially, again, this is all kind of fake because we're all on one machine, but the way to think about it is that each worker is executing that little chunk of code. There is an error that is the error that each worker you would encounter if you were just doing this on your own. That error is sort of buried in all of this gobbledygook that Spark decides to spit out at you. I will say that when we've used it, we've often written, one way, for example, just if you're writing a little library that uses Spark, and you were to have code that did stuff like this, you could, for example, get the first element from data and try to run the function locally. And if it throws an error, print a nice, happy, friendly error message. And if it doesn't throw an error, then execute on the whole thing. It doesn't, there are reasons that Spark doesn't do that for you, but you can do that, and that's very useful.
So along the same thread, so let's say I'm parallelizing across 10 elements.
Yep.
One of them fails.
Yep.
Is it possible to get the other 9 back?
No, not easily. You would have to you'd have to try catch inside your function, and then return none if it fails, and otherwise return the answer.
Every subsequent thing that it's mapping to would have to.
We would have to know how to handle none. Yeah, definitely. Welcome to distributed computing. Yeah, I would say error handling is one of the hardest parts, actually. It's really complex because, when you're working with real data, this happens all the time. You have 100 brains, 100 subjects, whatever. Because of the vagaries of data, it's going to work on 99 of them and not the one. Especially if you're doing stuff like, because again, map can be anything. Like map could be doing some crazy optimization algorithm, right? And that algorithm is stochastic, and maybe it fails 1/10 of the time for reasons that you can't anticipate. So you have to think about what to do in that case. You can just return 0, and then everything knows what to do with 0. Yeah?
What if robot depends on NumPy?
Ah, wonderful. So this is cool. That's totally fine, so long as, it's going to be totally fine here, so long as all the machines in our cluster all have NumPy. And that's basically all you need.
And Spark takes care of that for you?
So typically when you deploy Spark, you'll basically set up 20 machines that are all the same, and one of them will be kind of arbitrarily chosen as the leader, and the other ones are I don't like workers as sort of I don't like calling it that, whatever. Yeah, you'll have 20 machines and one of them's in charge, basically. So because all the machines are kind of the same in the typical deployment, they all have NumPy on them. There is a method, if you have some custom module that you've written and you just want to put it on all the machines, Spark does have this thing, add PyFile. So you can just do add PyFile, and you can pass it literally a .py file or a zip file, or an egg actually, that basically says, take this and put it on all the machines. Or you can literally just SSH on all the machines and install whatever you need. What I typically do in Spark deployments I've used is I just have all of them have Anaconda. So I just start up 10 machines, all have Anaconda, so they're all really likely to have basically everything I need. But yeah, beyond that, it basically takes care of it for you. So and it's actually, the code that it uses to do that isn't absurdly complicated, but if you do from NumPy import array, and then def robot hello equals array 1, 2, 3, and then you go to data.map robot, it will actually do some cool introspection to figure out that array came from NumPy, and then redo that import on all the workers, and just sort of do everything automatically for you. If you ever want a fun brain teaser, look up the part of the Spark code base that solves that problem. It's pretty crazy. So yeah, these are awesome questions. More? Questions about map? So yeah, maps are cool. You can write any function you want. It can be Lambda, it can be defined, it can come from some other package, and it can use anything that you have available on your machine and the machines that are running. And checking for errors ahead of time is really good because, as you saw, although you do see the error, it's not presented as cleanly as it probably could be. All right, so the other kind of fundamental operation, and again, if you get these two concepts, everything is sort of like one of these two. So the other one is called reduce. So the way to think about, so map was we took our data and then we applied a function to each element. Reduce is also, we also give it a function, but the way to think about that function is it's going to get applied on pairs of elements, basically over and over again until you only have one element left. Exactly what form that takes, is it a tree, does it happen one at a time, it doesn't really matter. Sort of semantically, the idea is we're giving it a function of two things instead of one thing, and it's going to apply that function of two things to all the pairs until you only have one thing left. And the classic example is addition. So let's do addition with a reduce. So we have data. Let's collect it to remind ourselves what it is. It's 1, 2, 3. One also useful thing for inspection is first. So data.first just shows you the first element. It's often useful. So we're going to do data.reduce, and then we're going to write lambda again, but now it's going to be a function of x and y, and we're going to do x plus y. All right? And we do that, we get 6. And we all, yes. Does that equal 6? Cool. So we've just added the numbers 1, 2, 3. Again, totally trivial. But we've done it through this reduce operation, which is, yeah, basically grouping these things together until you get down to one thing. So the reason that conceptually we've actually just covered like the core of distributed programming is that most things you ever want to do are kind of like one of these two things. Because the first one was applying a function to everything, but not actually returning anything back to us. All we did is sort of say, at some point, I want to apply this function to everything. Whereas here, we're saying, take the data and actually aggregate it together in some form. And the reason this is really powerful is that aggregation you can aggregate in all kinds of ways, and that function can be anything. But everything ends up being one variant of this or the other. How are we doing on time, Ariel? Are we chill?
Keep going. Take as much time as you need.
Okay, cool.
So the next session will start in 10 minutes.
Oh, in 10 minutes. Okay.
We'll start in 10 minutes. So
If the next speaker's ready in 10 minutes.
Oh, is that tall? Oh, okay, cool.
we'll start in 10 minutes.
Okay, great. All right, well, let's just keep going, and we'll see how far we get. So as I said, all of this is on the GitHub repo, if we don't get through it. So yeah, collections can be anything. We've just been using numbers, but one of the really powerful things about Spark is that these things we make, these lists, distributed lists, can have any content. So for example, if I start with my 1, 2, 3, and then I do map lambda colon ones, where so I'm just the ones constructor, and NumPy gives you a list of an array, and the shape of the array is whatever input you give it. What I get back is this thing that's again, it's a distributed list, but now it's a list of arrays, and the arrays are different sizes. So this is just to demonstrate these containers, these distributed containers, which is the right way to think about them, can contain anything. They can contain integers, they can contain NumPy arrays, they can contain objects, they can be all manner of sort of weird Python beasts. And that's cool because it makes it really easy to start integrating a workflow that includes NumPy, for example, with Spark. Your data could be a distributed collection of brain images represented as NumPy arrays. And then your map function would be a function that takes a NumPy array and does something cool with it. And you can also parallelize NumPy operations, which is getting back to the question that was asked before. So we actually sort of preempted that one. But this just makes it really explicit. So what we're doing here is we're importing from NumPy, it's literally your question, we're getting sine, pi, and round. We're now just making our normal data of 1, 2, 3, but then we're doing lambda x colon pi over 2 times x. And then we're mapping the sine function, and then we're mapping the round function, and then we're collecting it. So what we're doing here is actually pretty simple. We're just taking the numbers 1, 2, 3, multiplying them by pi over 2, computing the sine, which will give us something pretty predictable in this case, and then we're rounding, and then we're bringing it all back. So because we had pi over 2 times 1, pi over 2 times 2, and pi over 2 times 3, we got back 1, 0, and negative 1. But the real point to illustrate here is that sine was just some generic NumPy function, round was some generic NumPy function, this was just arbitrary data, and it all just works. So again, thinking about your own lives and your own workflows, you know, if these inputs are big and these functions are complicated, then this could be enormous improvement in speed. And in the best case, you actually, for this kind of thing, which we call embarrassingly parallel, you will get linear scaling in the number of cores you have available. So if this operation takes X amount of time, and then you have 100 CPUs instead of 1 across your cluster, then it should be 100 times faster. Now, in practice, it's maybe not quite 100 times faster, but it can often, in our own work, we've definitely seen it get up to that point. So that's cool. That's fast. Maybe because we're running out of time, I won't go through this example. But if you go to...
All the time you want to take.
Interesting. All right. Well, tell me if people are getting bored. What I was going to do is just show an example of actually getting real data into Spark, because one of the, we're not always literally just parallelizing the numbers 1, 2, 3. So there's a couple ways you can do this. One is you can use a couple built-in methods that Spark has for loading certain kinds of data. One funny thing is that these are not data formats that hopefully probably you will encounter that much. So it's a good way to just test it out. So here, for example, we're loading this iris.txt file. Iris is that data set everybody uses. So here it's just represented as a text file. And Spark natively knows how to read text files. It knows how to read JSON. It doesn't know how to read a lot of the things that you're probably likely to encounter. I'll give you right now 2 workarounds for that. One that's actually kind of cool is you can because we can parallelize anything, you can parallelize a list of files, and then your map operation can load the files. So for example, this is not actually going to work, but if I had file1.tiff and file2.tiff, and then I call map, and I have some function that loads TIFF files, this is actually a great way to ingest, as we call ingest, to get data into Spark. Because if you think about what's happening, once this whole thing executes, you have in parallel across your cluster now essentially loaded into memory however many images were in that list, and then whatever operation comes next, whether it's a map or a reduce or some other funky thing, it will just operate on that data in parallel that you loaded, and ultimately probably do something with it that will get your result back. Yeah?
What's the benefit of doing this overloading it locally and then sending it as an array
yeah, right. So you could instead load it locally. Basically, it's the fact that when you load it locally and then move it to all the nodes of the cluster, you're transferring a lot of data from one point to lots of points. So basically, depending on the networking on your master node, that can, and the size of the data, that can become very slow. So let's say you were like loading. Well, you don't run it. Actually, if it was this big, you could also potentially hit issues with just the size of the data on your computer. So if your data was going to be, say, 200 gigabytes, you don't want to load 200 gigabytes. You probably can't even load 200 gigabytes. If it was smaller, if it was like 10 megabytes, then loading it up and sending parts of it to all the workers versus loading it on the workers, it's probably usually faster to load it on the workers. Might not be a huge deal, but if it is, that gets really big, then not only might you not even be able to load it locally, but then transferring it will be really, really slow. That makes sense?
So in this example, the files are local on your computer, and you're assuming that those files, when unopened, are smaller than
no, yeah, oh good, okay, yeah. So in this case, there's a hidden assumption I didn't talk about. I'm assuming that whatever load TIFF is doing, it can run okay on all the nodes of the cluster. So I'm assuming in the way I wrote this, and that basically all the nodes of the cluster can access all of these files. Okay. So we can talk about like when will that be true, when will that not be true. So a case where it wouldn't be true is if you happen to store your data on your cluster so that the first 10 images were on the first machine, and the second 10 images were on the second machine, the next 10. So in that case, you'd have to do a little bit of special handling to basically, you'd have to kind of get into the weeds and tell Spark to do the first 10 on this one and the first 10 on that one. That's kind of an undesirable thing to have to deal with. In contrast, if you're, say, using cloud computing, say Amazon, and you're running this on Amazon EC2, which is Amazon's cloud compute, and your data is stored on Amazon S3, any node on EC2 can talk to data on S3. So if these 2 or whatever, 100 file names are just locations or pointers to data on S3, then any node on that cluster will be able to read them just fine. So basically, the other case it shows up, we leverage this a lot. So we have an internal Spark deployment we use with the research institute where I am, Genelia. We also do a lot with Amazon and Spark. So where we are, there's a networked file system, and all the nodes of the cluster, it's one of these like academic clusters, all the nodes of the cluster have access to that file system. So that's another way to make this very easy. But yeah, there's a crucial assumption that all the nodes can load data given a file name. Other questions? All right. this business is not super important. This one is interesting because it adds one extra concept that's worth being aware of. So actually, in a lot of treatments of this material, we would have at the very beginning talked about keys. I sort of deliberately didn't because I don't think they're quite as fundamental to a lot of our workflows, but they can be really, really useful. You asked a question about sorting?
Yeah.
Yeah, very important. That's a really good question. So in this case, I was doing what I was doing here was loading this text file. We can just bring up the text file. So here the text file looks like this. It's just literally every row is some numbers and then this name of the species. So what I'm doing here is I'm loading the text file using Spark. Again, it has some built-in methods for loading certain kinds of formats, in this case text. The very first thing we do is split it. So I just take that file and I split on spaces, just like basic text processing garbage here. And then, this is the important bit, to parse it, I'm calling map, as always. And inside the map, I'm constructing a tuple where the first entry of the tuple is whatever the fourth element of that line was, converted to a string, and the subsequent part of that tuple is a list of numbers, which is the actual data. So basically, I've taken this and I've turned it into a, again, distributed object where each element now, again, the elements can be anything, each element now is a tuple. And in this case where it's a tuple, we often talk about this thing being the key and this thing being the value. And the reason we say that is because there's a lot of operations actually built into Spark that can take advantage of keys. So what are some things you might want to use keys for? You definitely know one.
I'm just thinking like in terms of data matching, or when you get back something and you need to then associate it with another thing and you're getting it back in different order, then it's not.
Totally. Totally. Yeah, so a good one. Let's say we wanted to make sure whenever we ran collect, our data came back in the same order. Well, one really easy way to do that is to just make sure every one of our data records has as a key an integer, and then there's a Spark command called sort by key, which will just make sure that on any subsequent operation, we've sorted based on that integer, and everything will come back in the order that that integer specifies. So that's a really simple example of a sort by key, but it's a pretty common one. And in fact, when you're doing sort of array style manipulation in Spark, the keys can be a really useful way to handle things like data indexing and data sorting, and if you have two different data sets that have kind of similar indices and you want to put them together, you might need to use keys. So keys are really useful for that. You can also do some cool things like if you wanted to, are you ready, Tal?
I'm just sitting here like, I can't believe you just run over to the next session. Whatever I'm ready.
All right, great. We'll finish. Yeah, here's a cool operation. So reduce by key is just like reduce, except it does reduce, that thing where we took pairs and added them together. It does that only on all the things that have the same key. So if we, in this case, if we want to just count the number of elements associated with each key, all we do is we do a map to make the value 1, and then we do reduce by key. So what that's going to do is get rid of the data. We don't care about the data anymore. We're going to have a 1 for every data point, and then add together all the data points associated with each key, and we should get the number of elements that correspond to each of these species names. So this is, the API gets a little bit more complicated when you have map than just map and reduce. You have reduce by key, you have a few other things that involve keys. Map is kind of just map. Map values, sorry, only calls map on the value part and not the key part. That's what map values does. So basically, I don't feel Spark needs to be more complicated than this, though things you find on the internet might imply otherwise. I think it's a really useful tool. If you basically just replace all this stuff with like NumPy functions and NumPy data structures and file formats that you're used to working with, you could pretty easily probably start parallelizing a bunch of the things you commonly do in your data analysis. You just need to have Spark deployed, and how to do that might be discussed tomorrow, and if it's not, just reach out with questions. I'll be around. So thanks for listening, and yeah. Take it away, Tal.